I'm thinking of a number from 1 to 100. I'll let you guess the number, and each time you guess, I'll tell you if the answer is greater or smaller than the number you guessed. What will be your strategy? Okay, here's a bad strategy. Your first guess will be 1, then 2, then 3, then 4, up until you get it right. Worst case scenario, it'll take you 100 guesses, which basically is a linear algorithm, because the problem space has n elements and you're going through all of them. This is a bad strategy because it doesn't take advantage of the fact that I tell you whether the answer is smaller or greater than your guess. A good strategy would be a binary search. So what does that look like in this example? The strategy would be you guess the number 50, and then I say the answer is greater than 50. Then you guess 75. Now I say the number is smaller. Then you know the answer is between 50 and 75. So next, you guess the middle of those two numbers, which is 62. So you keep eliminating half of the possible numbers. You either guess correctly or you'll end up with one number, which has to be the solution. So that's binary search. Let's see another example, but this time you're searching an array to see if a value exists or not. We want to write a search function that determines if a value x is in this array. How would you do it? In this case, there's no choice but to search it linearly and just go through the whole array. That's because binary search only works if the array is sorted. Now that it's sorted, you can take advantage of that. The same way you took advantage of me telling you if a number is greater or smaller in the guessing game. So the binary search works this way. Assume you're searching for the number 72. If the search key is not equal to the middle element of the array, then you can eliminate either the left or right side from further consideration, depending on if the search key is greater or smaller than the middle element. In our case, 72 is greater than 32, so we can eliminate the left half of the array. We then again divide the rest of our array in half, jump into the middle, and compare the elements. 72 is greater than 71, so we eliminate the left half of the array. And then again, we go to the middle element, which is 88. 72 is smaller than that, so this time we eliminate the right side. And finally, we found it. Here's how we implement this code. The first parameter of binary search is a sorted array, because like I said before, to do the binary search, the array needs to be sorted. The function also needs the left and right index to search, and a number x, which is the value we are going to search for. The return value of this function will be the index of x in the array, and if the array doesn't have x, it will return -1. Like I explained before, to do the binary search, we need to jump to the middle, compare the value, and eliminate the left or right half of the array, and then repeat. First, let's get the middle index. We can calculate the middle index based on the left and right index. Even if we have an even number of elements in the array, it will round down when we divide by 2. Next, let's compare. If the value in the middle index is what we are looking for, then we'll just return it and end the process. But if x is greater than the middle value, we will eliminate the left half of the array. We will do that by reassigning mid to L. We know that the middle value is not x, so we'll exclude that too, by assigning mid +1 to L. If x is smaller, we'll just do the opposite. We'll assign mid -1 to R. This will be the last condition, and we'll just put that in an else statement. This process of jumping to the middle and comparing and reassigning L or R should be repeated, so we'll put a while loop around the whole thing. L and R will get closer as we loop, and we will loop until L becomes greater than R. We can express that in code by saying while L is equal to or smaller than R. So if L and R ever meet and become the same, that will be our last loop. If we cannot find X in the last loop, R will become smaller than L in the else statement, and the next loop will not run. If we cannot find x until L becomes greater, then that means we don't have x in the array, and we come out of the loop and return -1. What do you think the time complexity is for binary search? The time complexity is actually log of n, logarithmic time, which is way better than O of n, which is linear time. The reason why it's log of n based 2 is because each time you go through the while loop, you cut the problem space in half. So if you had 100 elements, the next loop, you'll get 50, then 25, then 12, 6, 3, then 1 or 2. That only took 6 steps, which is log of 100 based 2. A rule of thumb is, if there's an algorithm that is able to discard half the elements every iteration, it's a log of n time complexity. So this is the pseudocode for binary search using iterations. You can also perform binary search using recursion, but I'll leave that as an assignment. And I'll see you next time.